Okay, off we go. So, picking up from where we were last time, a real quick reminder, of course, don't forget about the attendance quiz, attendance code, all that business. And while we're at it, let me just remind everybody, I'm sure you already know this, but don't forget there's an exam on Friday. Right? Don't want anybody to have an unpleasant surprise on Friday afternoon. Okay, so let's see here. Yeah, so new section. There's different ways to come at this, different ways to sort of approach the idea of directional derivatives. I like this one the best because it's almost kind of a freebie. So here's the big idea. Y'all remember partial derivatives, right? Partial derivatives, we know bunches of stuff about partial derivatives. Partial derivatives are a slope of a graph. That's nice. Partial derivatives are a multiplicative factor. Now, with some specifics, when I say partial derivative, it's slope of the graph. Slope of the graph in which direction? Well, in the direction of the corresponding standard basis vector, right? Partial derivatives always mean in the direction of one of the standard basis vectors. Okay, fair. When we say multiplicative factor, it's what you multiply by input changes to get output changes. But again, the same constraint. This only works. That only makes sense if you're talking about a specific partial derivative, which is always in a standard basis vector direction. Okay, now here's another couple of formulas. We haven't written these down before, but these are still true. Kind of a strange one here. Claim that this is true. If you make a parametric line starting at the point A, moving with velocity, being a standard basis vector. And then if you look at the values of the function as you start at that point A and move, with velocity being a standard basis vector. And if what you do with these values of the function is you ask, well, how fast are the values of the function changing? By taking the derivative with respect to time. Keep in mind, time indicates your movement along this parametric line. It turns out what you get is exactly the partial derivative. Now, I'm going to say that that's intuitively satisfying. If you just think about what do we know about these things, the right side says, I'm at the point A, I'm moving in the direction of a standard basis vector, and I want to know how fast the function's changing. If you look at the left side, I'm at the point A, and I'm interested in how fast the function's changing as I'm moving in the direction of that standard basis vector. They pronounce the same, right? You read them the same. That said, this is a chain rule problem. I think it's a fantastic little exercise. Notice there's a composition here. F is a function of x, y, and z. X, y, and z are functions of t. And if you just literally write down the chain rule, plug in what you know, this will turn exactly into this. It's a great little exercise. Give it a shot. If you get stuck, not sure how to proceed, come talk to me in office hours. I'll be very happy to walk you through it. But nice point of view for whatever that's worth. And then here's a relatively easy one, also a little exercise that you kind of have to write down. But keep in mind the gradient is made up of all the partial derivatives. So if you dot with a vector that's mostly zeros and just a single one, that one is going to multiply by one of those partial derivatives. And so the answer is that partial derivative. So hopefully not a big surprise there. But again, write it down. Make sure you're clear on exactly all the details. Okay, let me say all this again just to kind of summarize. What do we know about partial derivatives? We know a partial derivative is a slope, it's a factor, and it's computed by that formula, and it's computed by that formula. Not clear why we would care yet, but bear with me. And the asterisk, the catch, again, is that this only works for standard basis vectors. Right? These vectors indicating the directions have to be standard basis vectors, right? Big catch. That's just what partial derivatives are. They're only in the directions of certain axes, whichever axis. Okay, now I want to I want to take a pause, and we're going to revisit this question of what is a standard basis vector. And let's look at this picture here. I've got various contour lines drawn here, you'll notice. And by the way, the picture's on either side. It's the same picture, literally copy-pasted. So on both sides of the line here, both sides of the page, we're looking at a hill. Right? And these are the contour lines. These are the exact same contour lines. And notice we have a couple of directions indicated, V and W. And let me point out, hills don't care about us. They're there. They were there before we were born. They'll be there after we're gone, let's hope. And they exist independently of our ideas. They exist independent of, for example, whatever coordinate system we should happen to make up. Right? So, the hill is independent of the coordinates. I can talk about directions. That direction, at a certain point on the hill, and saying I want to walk that way existed before people showed up and started talking about coordinate systems. Right? And likewise, this way made perfect sense and totally existed before people started talking about coordinate systems. So those things are real. That's intrinsic real stuff. So let's now ask the question, which of these vectors, V or W, is not just a unit vector. By the way, my intention was that these are all unit vectors. Which ones of them are standard basis vectors? Right? These are special unit vectors, or so we've thought of them in the past. So is V a standard basis vector? Well, you look at this picture on the left, and we've set up our coordinates. Perhaps the x-axis is east and the y-axis is north. That's pretty typical. Right? And, V is pointing in the direction of one of the axes. It feels like V is a standard basis vector. Right? Well, okay, yeah, but this axis system, setting up x and y like that's made up nonsense. I pulled it out of thin air. You don't have to do it that way. You are perfectly within your rights to set up any coordinate system you like. And I could say, you know what, I don't even know what you're talking about, north and east and west, and what is that? Who cares about any of that? I have no intentions of going to the North Pole. I'm just going to be hiking around on this hill, and maybe for whatever local reasons, maybe it makes sense to talk about these as being your axes. In which case, V, same vector. We're on the same hill, we're at the same point, we're looking in the same direction, nothing's changed. But now V is not a standard basis vector. Does that make sense? Everybody with me? So is V a standard basis vector? The answer is it's intrinsically, the question doesn't even make sense. Standard basis vectors are they're part of this little imagination that you make up called a coordinate system. It depends on your perspective. That's a you problem, right? It's not really intrinsic to the story. And likewise, this W here, don't get too comfortable saying that's not a standard basis vector. With this other coordinate system, it is a standard basis vector. Is that cool? So, what is a standard basis vector? Again, it depends on how you choose your coordinates, and any unit vector could be a standard basis vector if you just set up your axes right. Right? So now let's keep that in mind. Let's go back here to this story. We've got this idea of partial derivatives. Partial derivatives are defined in terms of coordinates. Right? xi is explicitly a coordinate. This is defined in terms of coordinates. So if I want to say I can't talk about coordinates anymore. I don't want to talk about coordinates. I just want to talk about things that are intrinsic. It's still true that these four things I have written in green are all equal to each other. That's true. I'm no longer sort of confined to these vectors only being standard basis vectors, because every unit vector could be a standard basis vector. If I want to be able to talk about these green things in relation to this W vector, and you say, well, you can't. That's not a standard basis vector. I'm going to say, well, you've made up a weird coordinate system. I like this coordinate system better. And by the way, now this is a standard basis vector. Does that make sense? So that's the idea. The big idea here is that forget about coordinates. These four things that I have in green, as long as you pick any unit vector, they're all going to be equal to each other. And sure, I can't call them partial derivatives because that's coordinate dependent. But these four, why do I keep saying three? These four things in green are always going to be equal to each other for any unit vector. So the big idea then is, well, let's just use a different name to represent these things. Let me do it like this. Pick any unit vector you like. Whatever. Go crazy. Any unit vector at all. I can choose a coordinate system in which it is a standard basis vector. And I could even at that time talk about partial derivatives, but I don't want to, right? But the point is, I could view this as being a standard basis vector. And so those four green things that we had on the other page are still all going to be equal to each other. So this expression, how fast is the function changing when I'm at the point A and moving with velocity v? Dot product of the gradient with v. Those will always be equal. They will always be the slope of the graph in that direction. And they will always be the corresponding multiplicative factor that you multiply by input changes to get output changes. This works for any unit vector because any unit vector could be thought of as a standard basis vector. So the punchline of what we've done here is we've taken this idea of partial derivative that was, again, we were very, look, this only makes sense if we're going in the direction of standard basis vectors. Now, yeah, you can go in any direction you want. Take a pick. Right? So this is a powerful concept. It's an amazing concept if you think about it. Partial derivatives, kind of, sort of, language issues aside, you can go in any direction you like. And this is worthy of having a name. So the name is directional derivative. And we use this notation right there. So that's the big idea. Big idea of a directional derivative is it's a rip-off of partial derivatives. How are we doing? Is everybody on board? Is everybody comfortable? We've got examples incoming. Okay, just a little bit more to do first. We've talked about partial derivatives, now directional derivatives, visualized like so, computed like this, are the slope of the graph. And so here's a graph of some function, and you're at some point A, and you look at the corresponding cross-section in that direction that you're talking about, and that slope will be that directional derivative. They're also the multiplicative factor, and now I'm going to make the observation that what you would multiply by ds or ds dt to get df or df dt, let's strategize here. What should I call this multiplicative factor? What would be the natural notation to use that I multiply by ds to get df? And I propose, I think this is extremely reasonable, I think df ds is a very reasonable thing to call it because you can't actually do the cancellation. It's a little uncomfortable, but this is one of these situations, like y'all remember many times doing in single variable calculus, it's actually perfectly fine to just kind of do a little faux cancellation there, and you'll get right answers. Right? Whether it's formally legal is not a problem. So another nice way to think about it. So again, sort of summarizing, pick any unit vector you like, any unit vector v. A directional derivative means when you're at the point A and moving with velocity v, how fast is the function changing? It gives you the slope of the graph in that direction. It gives you the multiplicative factor that you multiply by input changes to get output changes. You can think of it as rate of change of the function with respect to distance, not to be confused with rate of change with respect to time. Okay? And it's computed by this handy-dandy little formula right there. So we just got like a whole, we just developed an entire sort of machinery of this powerful idea called a directional derivative just by kind of ripping off what we already knew about partials. Okay. All right, so let's do one. How are we going to use this? Let's see here. Okay. I've got some function. We're at some point in the domain. And wouldn't you know it, the question says, what is the slope of the graph in a certain direction? We'll talk about the direction in a second. But the question says slope of the graph in a certain direction. So I say, oh, you want to know the slope of the graph? Yeah, let me do this in a different color. You want to know the slope of the graph? Oh, okay, well, I'm just going to compute the directional derivative because that's what directional derivatives do, among other things. And by the way, how am I going to compute that directional derivative? I think I'll use this super handy formula right there. Right? Slope is a directional derivative computed with a dot product with the gradient. So you'll see that's what we have right here. I'm going to compute the slope. It's directional derivative, dot product with the gradient. How are we doing? Everybody happy? Okay, here's one of the subtleties. You got to be careful about this. It just is what it is. But remember, this only works as described here. This only works if you have a unit vector. You got to be really careful. It's got to be a unit vector. Well, we were not given a unit vector. We were given a conspicuously non-unit vector. So we cannot take that vector v and start doing business with it. Here's what we can do, and this is an easy little patch. That vector, I can divide it by its own magnitude, and now I have a unit vector. I can totally apply the idea of a directional derivative to this unit vector. Oh, and by the way, notice we're interested in the direction that this vector points. This is a unit vector, but more to the point, this specifically is a unit vector that points in the same direction. So the direction that that red vector points, the direction that this blue vector points, they are the same direction. So this is a perfectly legal little hack here. Is everybody happy with that? Okay, so that goes there, which you see there. And everything else is kind of plug and chug, right? So we're going to need to compute this gradient. Gradient means you need to take the partials. Don't forget we're interested in what the slope of the graph is at this point 3, 1. So we've got to evaluate at the point 3, 1. And so you take 3, 1 and you plug into here, and there's your actual gradient at the given point. Arithmetic victory. Questions? Everybody good? All right, here's another one. This is very similar in a lot of ways. Excuse me, I thought I had a hiccup coming. Okay. All right. So we got a function t. This one happens to be temperature, whatever. And we got a formula. We're looking at a particular point. Notice what the question is asking is, what is dTds? So how fast does this temperature change per unit distance? Now, by the way, let's talk about that for a second. What do we mean by rate of change with respect to distance? What that means is, with a direction having been established, direction, of course, has to be established. Rate of change with respect to distance says, I don't keep track of time. I'm not interested in time. Forget about time. But for every foot that I step in that direction, I want to know how many degrees the temperature changes by. It doesn't matter how fast I move, right? It's just per unit distance instead of per unit time. Is that satisfying? Is everybody on board with this idea of dTds? All right, and how are we going to compute that? Well, that is, need to do like this. This thing that we're interested in computing, derivative with respect to distance, is another one of my interpretations of directional derivative, which again I am going to compute with that handy formula, dot product with the gradient. So again, just like the previous question, just like the previous example, I just observe that what I've been asked happens to be one of these several interpretations of this new construction called the directional derivative that I have a convenient formula for, right? So you acknowledge, doff the cap that this is one of our interpretations of directional derivative. Recognize that we have this formula for computing directional derivatives. And again, it's all kind of plug and chug. Don't forget to make your vector a unit vector. You see I did that here. A little bit of calculus, a little bit of arithmetic. Everybody's happy with all that? It's hard for me to tell the difference between, satisfaction and confusion. No questions? Feel free. All right. Okay. That's a pretty straightforward idea. I'm a fan. There is an awkwardness I have to bring up. This is unfortunate. There are just certain situations where, sadly, the conventions are not standardized. And there is a different take that can be used on directional derivatives. And it's a very common different take. The different take is to remove the requirement that it be a unit vector. Now let's think that through, okay? Can you do that? Well, whoa, not with how we've described things so far. Right? The way we've described things so far, we were just talking about picking different axes, right? And when you pick different axes, the vectors don't change. Unit vectors remain unit vectors. What we've concluded is only for unit vectors. So if you take away these vectors being unit vectors, we're dead in the water. We don't know what's going on. Right? If you say, well, we're only going to consider any other vector, forget about it being a unit vector. Well, here's the bad news. You can no longer interpret as dFds. You can no longer interpret it as a multiplicative factor. You can no longer interpret it as a slope of the graph. Kind of seems like there's nothing left, right? But in fact, there is. There's something really, really useful still left here. I can still say that this thing right here, let me zoom in so we can focus on it. Whoa. This thing right here, I'm at the point A. I'm moving with velocity v I'm interested in the values of some function and I want to know how fast they're changing. That's still a very natural scenario to want to be interested in. Right? In fact, I would point out, when you are at a point A and moving with some velocity, how often is it that that velocity is actually a unit vector? I would point out that's a very narrow thing, right? It's a very narrow consideration. So the idea that we would allow this to be any vector, very tempting, very, very nice, very valuable. And the great news is that this formula here is still true. Right, so this very natural question, how fast is the function changing when I'm at the point A and moving with velocity v, I can still compute with this. Super easy. Compute the gradient. It's just partial derivatives. Dot with your velocity vector. It will still answer this question. And so the idea is, well, let's use the same notation and the same terminology. They call this also a directional derivative. Now, obviously, these are inconsistent, right? This is a different convention, different assumptions, different conclusions, and it's very unfortunate that the two different camps here use the same terminology. And I'm sorry, it's not my fault, right? I didn't create this scenario. I'm just letting you know what to be aware of. So the punchline here is y'all have to be heads up on this. Right? Outside of Math219, I have no control over what terminology people use and what notations people use. And by the way, there's various different notations for how to write directional derivatives. This one's very common. Some people prefer to write the V as a second parentheses after the A, whatever. There's various different notations. But you have to look at the context. If you're talking to someone and they say, hey, well, let's directional derivative, I would advise that you ask them, hey, by the way, are you, when you say directional derivative, do you believe that that has to be in a unit vector direction, or are you open to it being any vector, and what are we doing here? Make sure you know what they're talking about, because otherwise there's a huge potential for confusion. Okay. All right. For the record, just for, two things I should say here. Let me erase all of this. I want to make it clear what our course policy is. In Math219, we have to pick a standard. We've got to stick with it, and we've got to be consistent. And as I've learned from personal experience, teaching a class with a convention about an important construction that's inconsistent with the book is a nightmare of confusion, and I don't think it's a good idea. So whether I like it or not, we're sticking with the book on this. Right? So the book sticks with unit vectors only, and for unit vectors v, defines directional derivative indicated with that notation, understood with that intuition, computed by that formula, which gives you the slope of the graph and the multiplicative factor in df ds. Right? That's the convention that we're going to be using in Math219. Perfectly clear, right? Is that perfectly clear? Any questions about, okay, so this is unit vectors only for the purposes of this class. And with that said, let me just recognize, outside of Math219, if I were doing some math business, I actually kind of prefer the other convention. Pros and cons. But anyway, this other convention is not some sort of crackpot, weirdo thing at all. Okay. All right, so heads up about that. Oh, and by the way, here's a great exercise. I think this is a really useful exercise. You can totally do this. Notice that when we say we're at a certain point and moving with a certain velocity, we're describing a parametric line. And when we say we are interested in how the values of some function f are changing, altogether we're talking about a composition. And if you write down let's see, I want to get this all on the screen. If you write down, with all that in mind, if you write down this expression, and if you simply apply the chain rule to compute it, as indicated by this little composition here, what you will find is that you reproduce this formula, namely that df dt is gradient dot velocity. So you will get this right here. df dt is gradient dot velocity. So this is a nice exercise. Again, just write down the chain rule as applies to this diagram, and you'll show what I previously claimed. Okay, moving along. We're going to talk about some nice properties of gradient vectors. Turns out there's some really cool things to say about gradient vectors. And it turns out that directional derivatives are a great segue into these nice properties of gradient vectors. So we're going to just do these one at a time. The first comes to us as a question. Suppose that I'm looking at some real valued function. Suppose that I'm at a certain point A here in the domain, and suppose I'm entertaining all the different directions from the point A that I might start moving. And by the way, I like to think of the point A as being where I am, right? That's me standing there, and I'm thinking about which direction I'm going to start walking. And for whatever it's worth, my favorite metaphor on this, I like to think of the function as representing temperature. So I'm out in the woods somewhere. This is me. I'm going to start walking in some direction. I don't know which direction. I'm trying to figure out which direction should I start walking, and why. How would I decide which direction to start walking? Well, look, the temperature. I'm cold. I want the temperature to increase as fast as possible. So I want to figure out which direction to walk that makes the temperature increase as fast as possible. Or said differently, I want the directional derivative to be maximized, right? So I want to figure out how to make that directional derivative as big as possible. So among all these different unit vectors, which one specifically, which direction do I go to get the maximum rate of change of, let's say, temperature? Does it seem like a reasonable question? Imagine you're out in the woods. You're cold. Which direction do you go to warm up, right? The natural question you want to ask. Okay, now I'll show you how to answer that question. There's a very crisp and elegant answer to that question, but let's talk about the terminology a little bit. The direction that you go could be described by different names depending on how you interpret the directional derivative. Right? If you interpret the directional derivative as slope of a tangent line, you end up with this terminology here. I mean, you think about it, if it's a slope, which direction makes the slope of the tangent line as steep as possible? Direction of steepest descent. It's pretty natural terminology. It's a very common terminology. It's probably the most common term for how to describe this vector that we're looking for, the vector that maximizes the directional derivative. So direction of steepest descent, you're going to hear all the time. I have to point out that only makes sense if you're looking at a graph, because directional derivatives are slopes of graphs. So this only makes sense if you're looking at a graph. If you're not looking at a graph, it doesn't make any sense at all. So I like this other term. Let's think of our directional derivatives, the thing we're trying to maximize, as rate of change of the function with respect to distance. And if you make the rate that the function is increasing as fast as possible, direction of fastest increase is the natural resulting terminology. That's my preferred term. I will usually say direction of fastest increase. Be warned, again, some people like to say direction of steepest descent. Nothing wrong with that. It's just narrow. in making sense. So anyway. Okay, let's do it. How do we actually do this? It's not that big a deal. This is what we want to maximize. That's how we compute the thing that we want to maximize. Notice it's a dot product. This is how we compute dot products. Right? Keep in mind, I'm only looking at unit vectors because I'm interested in directions. Right? Magnitude. It wouldn't make any sense to have non-unit vectors here. Non-unit, that just says go faster. Right? I already knew that. I'm already planning to walk or run as fast as I can to get warmer. That I understand. I just want to know directions. So unit vector, that means that this factor there is a 1, so we can throw that away. And then the last little subtle point, keeping in mind we're at this point A, that's where I say I'm at that point A, that's me. And I'm contemplating, maybe I'll go that way, maybe I'll go that way, maybe I'll go that way. I don't know. There's a lot of different directions that I might go. I'm still thinking about it. You notice I haven't moved yet. I'm still at the point A. Once I decide which direction to go, then I will start going, right? But at the moment, I'm just standing here, so A is not moving, otherwise known as A is fixed, aka A is constant. And notice the gradient is computed at the point A. So if A isn't changing, that means the gradient isn't changing, and that means that the magnitude of the gradient, while we contemplate different directions, that magnitude of the gradient is not changing. Right? So altogether then, the way I'm going to maximize the directional derivative, I just have to figure out how to maximize cosine theta. If you can maximize cosine theta, you win. And of course, that's an easy trig problem. We maximize cosine theta by making theta equal to 0. And don't forget what theta is. Theta is the angle between these two vectors, gradient and v. And now, geometric appeal, if I want to know what does it look like, which one of these vectors is it that makes that angle 0? Well, you make that angle 0 by picking v to be that unit vector, the same one, the one that points in the same direction that the gradient points. How we doing? Everybody see it? Okay. So nice punchline. Actually, let me say this: very nice punchline. Weirdly nice punchline. Where did the gradient come from in the first place? Do y'all remember? It's a while ago at this point, but think back to when we first started talking about the gradient. It was a notational convenience, right? We were writing down linear approximation formulas, and there was a bunch of partial derivatives that it would kind of in the structure kind of looked like a dot product. We just made up this thing called the gradient as a notational shorthand, just as a convenience. And what we see now is, but it's geometrically natural. It points in the direction that makes the function increase the fastest. And that's an eyebrow raiser. When you write something down for no particularly good reason, and then it turns out to be the right answer to a natural question, what are the odds? Everybody okay with that? I mean, I think that's worth taking a moment to think about. All right. Okay, natural, next question. This is the direction that makes the directional derivative as fast as possible. Okay, fine. How fast is the function increasing? We've decided we're going to go in this direction. How fast will temperature, for example, be increasing? And okay, immediate computation. There's our formula to compute directional derivatives. here's the vector that we've decided to use. Plug that in. Notice the dot product is a magnitude squared. Then the magnitudes cancel, and a nice punchline then, the answer to the question, how fast is the function increasing? Well, the magnitude of the gradient. So again, what the, oh my God, how did this is so weird. This little notational convenience called the gradient, its direction is the best direction, and its magnitude tells you how fast the function's increasing in that direction. And one little refinement of what I just said, being as it is a vector, the gradient has exactly two geometric features. It has nothing more than a direction and a magnitude. Both the direction and the magnitude are natural, right? They're the answers to reasonable questions. And so the gradient itself can actually be defined as such. I don't recommend it, but you can very reasonably say that we define the gradient to be the unique vector that points in the direction of fastest increase and whose magnitude says how fast we're going in that direction. Very reasonable. And it's certainly, even if you don't use this as a definition, and again, I don't recommend you do, this is a great way to think about the gradient. It points in the optimal direction, and its magnitude says how fast the function's increasing. Okay. All right. Let's see how to use this. It's such a powerful result. The way we are going to use it is going to be very plug and chug. We're going to ask the questions that we just answered, and the answer is going to be compute the gradient, pretty much. So here we go. We have a hill. The hill is in the shape of the graph. Keep in mind a graph is that very specific construction, z equals f. And given a particular place where I am on the hill, I'm going to ask very reasonably, hey, which way is uphill? And how steep is it? And the answer to both of these questions is gradient. Which way is uphill? Well, what direction does the gradient point? That's the direction that's uphill. How steep is it? Oh, well, the steepness is the magnitude of the gradient that you already just computed. So that's how steep it is. And by the way, that's really steep. Right? That's like 2.8. Like that. It's very steep. Plug and chug, pretty much. Does that make sense to everybody? Now there's a subtlety on here. I do want to talk about the subtlety. This is easy to get confused on. So here's me. I'm standing on the side of the hill. I'm a three-dimensional critter. I, therefore, am at a three-dimensional point that has three coordinates, x, y, and z, right? And yet, even though my location has three coordinates, x, y, and z, when I get on the radio and radio back to base camp as I'm climbing this mountain, I'm going to describe my location with longitude and latitude. And that's how people talk, right? If you're out and about on a Friday evening, Saturday evening, whatever, and someone says, "Hey, where are you?" And you say, "Oh, I'm at the corner of 9th and Main." They don't ever come back and ask you, "Yeah, but what's your altitude?" Right? Why would they? They know your altitude. You're at ground level, of course. If you hadn't been at ground level, that would have been a big news item. You'd have said, "I'm 50 feet underground." You would have said something, right? It's understood that you're at ground level. So, nevertheless, we have to recognize the point in 3 space where you actually are, and the point in the domain that is going to be the point that you plug into the gradient, because that's also the point that you plug into the function, because this function is defined on a two-dimensional domain. These 2 points are not the same, right? And yet, very commonly, we will use the domain point as basically a convenient way to talk about your location. And sometimes you're given the map coordinate, what you might call map coordinates, and you have to infer the actual location. And so don't forget to compute z, and that's the third coordinate giving your actual z, right? And sometimes it goes the other way. Sometimes you're going to be given the three-dimensional coordinates on the hill itself, and you need to figure out what do you plug into the function, and you have to, it's your job, right, as students to realize, oh, that's the point on the graph. I need the point in the domain, because that's how the function works and that's how the gradient works. They're defined in the domain. So people conflate these, heads up, and if the one that you're given isn't the one that you need, you have to convert accordingly. Does that make sense to everybody? It's subtle, but it's just kind of the reality of the situation. Did I see it? Yeah, go ahead.
Does the gradient tell you anything about the direction of steepest descent?
Yeah, absolutely. So that is kind of the point. So which way is uphill is really kind of, that's the more natural way to describe, when you say direction of steepest descent, it just means uphill, right? And yeah, the gradient always points in the direction which is the direction of steepest descent. Yep, that was the conclusion from...
No, I thought it points in the direction of steepest ascent. Are you allowed to assume that the direction of steepest descent is the opposite?
Oh, I'm sorry, I misheard you. I'm sorry, you said descent.
Yeah.
Sorry, thank you.
Theta equals...
I withdraw everything I said before. Sorry, I just didn't hear that. The direction of steepest descent is always exactly the negative. It's exactly the opposite of the direction with the gradient points. So, and my best intuition for that is when you're hiking, the direction that is uphill is always the negative of. It's always exactly the opposite of the direction that's downhill. Right? Does that make sense? Yeah. So yes, absolutely. Yep. Yeah.
What if I'm on a plane it goes like this, and on a point you're can the descent be higher than the ascent?
I don't understand. Sorry.
Can we have different the steepest direction of steepest ascent can be not the opposite of this descent?
No, they'll always be opposite. Assuming our function is differentiable, they're always opposite. Now, one thing to keep in mind is that we're just talking about what's happening at a single point on the surface, right? So if the surface has a different shape over here, maybe, okay, that's not what we're talking about. We're just talking about at one single point on the hill, aka at one single point in the domain. And yeah, uphill and downhill will always be exact opposites of each other. Yeah. Right. Okay. Let's see here. This is actually a pretty good stopping point, so we will draw the line right there. Y'all have a good rest of your Wednesday. Good luck studying for the exam. See you on Friday.
Is 2.6 covered in the exam?
Give me a second here.